Okay, cool. Thanks, Elizabeth. Okay, thanks, everyone. It's great to be here. Okay, so this is the title I was given. I was told I could modify it a bit, so I put in cosmology and galaxy formation. I think probably most people here work on cosmology and galaxy formation type of simulations, if they work on simulations, so hopefully that's okay. I should warn you that I am going to make some ChatGPT jokes. I know some people might groan, and it might be bad for some people, but we haven't had too many so far, so hopefully that will be okay. All right, so anyway, the work that I'm going to show from people that I've been lucky to work with includes all these people up here. It's supposed to be a review. Obviously, I'm going to be heavily weighted maybe to stuff I know more about, but I'm trying to be fair to everybody. There's a lot of amazing work, which maybe I won't be able to give justice to all the work that's been done on this. Okay, so the definitions here that I'm going to use, the standard ones, right? So simulations in this context will just be computer models that start from cosmological initial conditions, and then deep learning will be neural networks. And as with all of these things, a lot will go down to the training data. Everything goes back to the training data, and that's one of the issues that we're going to have to discuss, I guess. Do we have enough training data? That's always the problem. Okay, so imagine we had some perfect simulation machine that you want to simulate the universe, right? This is what it looks like, apparently, according to DALL-E, all right? This is a perfect simulation machine. It's going to do things for us. It's going to explain everything about the universe and solve everything, right? So what different things do we want our simulation machine to have? Well, what we like to do is we like it to simulate the entire universe, hopefully, at the resolution of one atom, maybe, or even less, okay? But at least we want to have a large volume, large enough to get around cosmic variance. We want to include all the physics that we know about, all the lab physics that we've got. We like to simulate any model that anyone has come up with, any sort of obscure cosmological model, any other kind of model, any model of subatomic physics. We want to be able to do that. If we can't actually resolve everything, we like to have subgrid, so below the resolution, that also works perfectly, that would actually reproduce what you would do if you had infinite resolution, right? And then, of course, what are we going to use this simulation for? We'd like to have inference. We'd like to be able to understand and constrain what's going on physically, okay? And, okay, it's a perfect machine. We'd also like to be able to run it actually with no energy, right? We've already heard a lot about the carbon footprint of things, and I'm going to show you a few things in this talk as well. We'd like to be efficient and basically not destroy our planet by trying to understand it, I guess. Some other things we like to do, we like to try and explain what's going on, and this again, along with how much training data do we need, the fact that we can't explain what's going on inside of neural networks, at least not easily. There are many ways of trying to do that. That's something that we'd like to be able to do. It's not clear if we can get there or not. And then related to that is, can we actually trust the results, right? And can at least we quantify the uncertainties, our relationship with the systematic and statistical errors quantitatively. And we like it to be very fast. And also we'd like to have low storage needs, right? Which will be important as well. Okay, so we add neural networks to solve all of these things, right? Neural networks make everything better, apparently, right? And so we need to know where we're going to put deep learning into this workflow of our simulations, right? So here's some different things you could do with cosmological simulations. Obviously, you might start with some initial conditions, go through, you could add different pieces of physics, make mock summary statistics, and all of these boxes, people have tried to put neural networks, deep learning in there to improve them in some way, right? And there are also ones that maybe people are even more enthusiastic about, like putting them into the initial part, the grant proposal, right? And the one I really like is putting them into the grant report, using those. And, so warning, ChatGPT joke coming up, right? So you might say, okay, ChatGPT, give me a grant report for my NSF grant, but it has to rhyme. And ChatGPT can't even rhyme. Look, even the first line doesn't rhyme. Does delved rhyme with melded? I don't think so. Okay, so anyway, I tried again. This is the one I actually used. Please write it in the style of a pirate. Okay, our matey, with the wind in our sails and the hardy support of the NSF, we embarked on a cosmic adventure. I particularly like employing simulation-based inference like a trusty compass. Okay, so anyway, hopefully my grant program manager liked that one. But anyway, I recommend it, make their life more interesting. Of course, they wouldn't read the report anyway. But. Okay, so lots of people have sort of given it some sort of broader picture background, right? So obviously we're living in a very rapidly changing world. We're all aware of that, right? So we could just have a look and step back and compare what's been going on in the world of AI, deep learning, with what we've done in simulations over the past few years. So this thing is showing you, hopefully you can see, this is how well deep learning can compare to humans on various problems, including handwriting recognition. So, I refuse to believe that a neural network could understand my handwriting. So I can't believe that it can get to 100%. So I want to break this because I can't understand my handwriting when I've written it. So, but you can see that these things are getting steeper and steeper. People are solving problems quicker and quicker, right? So image recognition, speech recognition, all these things, right? So it's not even clear it's exponential. It's basically vertical, right? So what about simulations? Well, in simulations, we have exponential increase. For example, we can quantify it by the number of particles. Again, this is a nice compilation, I guess, by Florent Leclerc, who's here, I guess. Is in Paris? Okay, well, he's here then. So anyway, you can see here's the number of particles as a function of year. And this is exponential, right? It's a log linear graph. And you can see basically that you could decide, in the other one, there was different tasks that deep learning can do. Here, these are different methods that we employ to solve gravity plus dark matter simulations, but you could also put it on at roughly similar intervals, new physics that we've added, for example, early on gas dynamics, for example, subgrid star formation, black holes, magnetic fields, things like that, right? So you can compare that, which is obviously a data quantity question, the number of particles in a simulation as a function of year. You can compare that to the training data set size for large training data sets for deep learning. And you can see, for example, here the GPT models up there, basically how many pieces of information they use, right? So this is basically how many words were used to train large language models. These are also other training data sets as a compilation, basically different sorts, apart from language models, also image models and other things. And you can see that this has risen quite steeply. It turns out that we're now at the stage, if you plot both on top of each other, these are the particles per year in cosmological simulations, and you can see that the training data set sizes are now comparable, okay, to the simulation data, right? So you can see that obviously this was a rapid rise, and now we're using similar amounts of computer power basically to do the largest cosmological simulations. And also that means that if we want to train our data, okay, we basically reach the limit from the simulations of the amount of training data that we can actually provide, right, compared to the models. Okay, so one thing I wanted to say also is that we're in this context of deep learning and industry driven, right? There's a lot of 2D stuff out there. And as cosmologists, we live in a 3 or 4D world, right? So we like to use 3D models as much as we can. And a lot of the work that people have done is converting algorithms in the literature from 2D into 3D. And so there was, for a couple of years, there was a lot of 3D generative modeling in the literature because of the metaverse, right? And the fact that we're all here in person and not like with our headsets on means that obviously didn't work so great, but there is some good material that was produced because of that. There was obviously a lot of money in that, so that's where that came from. But the first work on generative simulations in cosmology was actually in 2D, right? So this is the first paper that I could find. I don't know if it is I don't know, Paco, do you know it's the first paper? So Rodriguez et al. And so here, they've got a generative adversarial network, which is generating image slices after having been trained on an n-body simulation, right? And so generative adversarial network, okay, so we could draw a diagram of that. And so I asked a neural network to draw a diagram of it, and this is what it came up with, right? This is the usual thing. So this is DALL-E's interpretation, draw me a generative adversarial network. You might say that's not fair because DALL-E is actually a transformer. So I'll ask DALL-E to draw a transformer architecture, and that's what it looks like. So there we are, that's great. So remember, when you're looking at these things, you might be laughing like, okay, I can tell it's silly. That's because you're a human, right? Okay, but if you were looking at this, maybe this is just equally bad, right? It's just that you're not trained to actually understand how this relates to the physical universe, right? So there's a slightly serious point there. Okay, so the generative adversarial network, okay, this is one of many generative AI techniques that can be used in all fields, including cosmology. And as this audience, you guys know how it works, right? So you put in some random noise, and then you have a generator, and then a discriminator, and it tries to tell from real data and fake data, and it improves through backpropagation until you're generating something that the discriminator can't tell apart. And there are other generative architectures that have been used in cosmology. There's a diffusion, which I'll show some examples from. There's also a newer Poisson flow model, and there may be some other ones as well, right? But they all are generative models. And so as generative models, I'd like to just draw the distinction between a generator and an emulator, just in this context. So for our purposes, for our definition, we'll say generator is something that starts with noise, okay, just random noise of some sort, and then it produces an example of something that's generated, right? If you put different noise in, you get another example. And if you look at the cross correlation, and we've already seen in several talks, the cross correlation or the correlation coefficient of the individual Fourier modes in these two examples, because they started from different random noise, they will have a zero correlation, okay? And so this is something that's generated, right? An emulator, in this case, the emulator wouldn't start with noise, it would start with something, initial conditions, and then you get some emulated final state, which you can then compare to the true final state. And again, this is something that we've seen before. And here, the correlation coefficient of the Fourier modes on large scales generally is pretty good, and then it gets worse as the emulator has trouble dealing with smaller scales, right? Okay, so you have to remember, as with all these things, that both the generator and the emulator, they both need to be trained with data. Okay, so how well they can do depends again on the quantity of this data, and evaluating really how reliable it is. You need to basically decide how much data you actually trained on, and there are various ways of doing that, but it's one of the big issues that we face. Okay, so those were field level generators and emulators. Here's an example just of an emulator of a summary statistic. And so you can use a neural network to actually emulate the summary statistic itself. And so Daniel gave a great talk this morning about the CAMELS project, right? They've over 60 papers, I understand, already published on that. It's this giant data set of training data and applied to many different problems, including, for example, here's the star formation rate density as a function of redshift, and the neural network has learned from this large set of training data, marginalizing over parameters, and then giving you a star formation rate compared to the truth in this case was the illustrious TNG simulation. Okay, so going back a little bit in ancient history for deep learning, this is 4 years ago now. Okay, so this is what I think was the first emulation of simulations at the particle level. Okay, why particles? Because a lot of simulations, particularly if we're working with dark matter, they run with particles, and it'd be nice to be able to emulate or simulate or generate particle distributions, right? And so in this case, this is an emulator, which basically learned, a neural network again, learned how structure formation works, basically by being trained on large sets of initial conditions and final conditions. And then you can compare to the ground truth, the PM code in this case. And you can see that back 4 years ago, they were comparing 2LPT, Lagrangian perturbation theory, and you can see that the PM code is almost the same as this emulator d cubed m. And again, the cross correlation of Fourier modes here, we've got 1 minus the correlation coefficient squared. So if it's down here, it's good, okay? And you can see that at almost a k of 1 inverse megaparsec, it's basically the correlation coefficient is better than 10%. Sorry, it's better than 90%. And so it's doing pretty well all the way down to k of 1. So remember, when you're talking about these things, nonlinear scales, they happen. This is sort of the canonical linear scale that people say, okay, we'll think of everything this way as linear. And then down here, we're in the nonlinear regime, maybe by an order of magnitude. We'll see in some other plots how far people can go. Okay, so let's go back. So we had this weird simulator machine that includes simulation plus neural networks in various points. Okay, now we really would like to do this. We're always limited by resolution and volume, right? In cosmology, we always want bigger volume. We always want higher resolution, right? Also, we want it to be fast. We don't want to, be waiting around for hundreds of millions of hours like we are. That's why we invented parallel computing, but also we want the algorithm to be fast, and we don't want it to have to store too much data as well. And so one way of doing this is to run a regular simulation that's computationally cheap but low resolution, okay, like, for example, that PM code I just showed you that was used before for testing. And then below the resolution, when it starts to get really expensive, use neural networks, deep learning to add in the fine details, okay? And so we really want to roughly balance the time taken in these both these pieces, because obviously we don't want to run, you know, a simulation that takes 1 million CPU hours and then do 10 hours of deep learning on it, or vice versa, right? And if we combine these two, then this is an AI super resolution simulation. So super resolution is done by the neural network. And so the first paper on this, I think, was this nice work by Cody Romano et al. Again, this is about 3 years ago. And this was based, the simulations are particle-based, but this was based on voxels. Okay, so the simulation was put onto a grid. And then again, we have this GAN architecture, okay, where basically you're giving not only, instead of giving noise as the initial condition, you give, in this case, it's an emulator. So you give initial conditions at high resolution, and you give a low resolution simulation at the time step that you want to simulate, right? So this is the one that was computationally cheap, okay, say a PM simulation. You give it that, plus you give high resolution initial conditions, and then when you're training the neural network, you have a training data set which is real high resolution simulations. And then again, you have to decide how to compare. So a lot of people use this Wasserstein loss, and again, with the magic of backpropagation, you get the weights working, and then your GAN ends up producing an emulated simulation at high resolution. Okay, and so this work here increased the spatial resolution by a factor of 2. So this was a GAN. There's also work that's been done more recently with denoising diffusion models. Okay, and so these 2 nice papers here that are doing a similar thing, and they have some other advantages as well. Here is a particle-based simulation for super resolution. The one I just showed you before, you had to assign the particles onto a voxel grid, and then so you could only simulate a grid of high resolution data. You couldn't simulate a particle-based simulation. So here, this work led by Yin Li took the same kind of approach, but the output format was particles. So here you're working with Lagrangian displacements and trying to predict those instead of the density. Okay, and as a result, the output format is exactly the same as, say, an MP gadget, in this case, simulation. And so if you wanted to, you could take the output from this generated model and then run it with MP gadget. And I'll show you what happens when you do that in a second. But here, we enhance the spatial resolution by a factor of 8, which means 512 cube more particles. And you can see from up here, you know, it makes a difference to the density field. You know, this is the low resolution input, and here's the super resolution output. And you can see that you can get these sort of subhalos forming. And the nice part is that it is fast. This was a 5,000 cube simulation, and it took 16 hours on a single processor, right? Well, on a single GPU at least. So, you know, that would take maybe 10,000 times longer if you ran it with an n-body code. Okay, and it can generate subhalos. This is a generative model. It's not an emulator at this point. And so you can see, for example, here's the true high resolution simulation, and here's the super resolution one. And then up at the top is the low resolution. And you can see here that the small galaxies are in different points in the super resolution compared to the high resolution, just because they're put in, generated on the basis of random noise initially, right? But statistically, it can get the mass function to within about 5% at these masses. So what could you use these things for, right? So I'll come back maybe to the best use cases later, but here's something you could do. If you've heard about fuzzy dark matter simulations, where they include quantum pressure, they're incredibly difficult to run. They're very, very time consuming. But if you could somehow train, if you could train super resolution simulations using high-res quantum pressure simulations, you could then run many, many realizations very quickly. And this is some work that was done by Mary Sipp and Patrick Lachance over an undergraduate summer project. And basically the super resolution ends up adding in small halos in the CDM, and in the fuzzy dark matter, they're not present. And so this was actually an easy case for this. And so one of the great things about super resolution is that the amount of training data you need is actually not as big as you might think, just because the low resolution simulation does a lot of the work, right? And then you end up only looking at small scale variations when you're training. And those small scale variations, there's obviously many, many, many independent volumes inside your simulation volume. And so that's why it's actually a good approach to minimize the amount of training data you need. Okay, so all those examples were trained on a single redshift, okay, and then the neural network can only produce a single output redshift. And if you want a different redshift, you have to retrain. And so an approach that you can use instead is to try and give the neural network data, training data from many, many different redshifts at once, and also give it the redshift itself when you're training, right? And that's a style parameter in a style GAN. And so, for example, here you might have a low resolution simulation noise plus the redshift Z1, and then here redshift Z2. Here you would get two different redshifts, but if you train on many, many redshifts at once, it turns out that as long as you keep the same noise, the time evolution of the fields are actually consistent. Okay, and so this is some work by Xiaowen Zhang, who's here. What you can see is that if you've kept the input noise the same, okay, but the low resolution field changes and the redshift changes, but the simulation has been trained on many, many different redshift snapshots, and it can actually produce, for example, here's the power spectrum at many different redshifts. You just tell it what redshift you want. And you can even track individual subhalos as they fall into halos. And remember that each point along their trajectories, the small scale structure is being generated by the GAN, but it actually knows how to keep a consistent history. And you can even build merger trees, for example. And so here's a merger tree at the top one. This is the true high resolution merger tree. And the bottom one is an example generated merger tree where you've got the most massive halo any redshift is this red dot. And then there are all these things that have fallen into it, and they're all tracked by the GAN. And so somehow magically, as long as you keep the noise the same, it feeds through the dynamics and then gives you a consistent merger history, which is, something that I'm not sure if we expected or not. Okay, so Xiaowen, who's here, and Patrick as well, they got a poster here with the next thing we're trying is to make this into an emulator. So remember, we had this generative model where the super resolution model on small scales, it just has random realizations of small scale structure. What you'd really want is to have exactly the same structure, okay? So for example, here's the high resolution model. This was the input low resolution. And you want somehow to emulate, and so have exactly all these halos in the same spots. If your emulator could do that, then you'd have to worry a lot less about the training data if you could prove that it gives you exactly the same structures every time, right? Rather than if it gave you a random realization, you're always wondering, is that some freak realization? Is there something wrong with it? And so that's what Xiaowen and Patrick are trying to do. And here's an example of some sort of effort. It's ongoing work, but here's the original super resolution, which has random structures on small scales. And here's so far an emulator. Basically, there's the addition of an extra layers with a different loss function after the discriminator. And some of the structures, you can see are sort of pretty similar now. It's doing pretty well. Here's the cross correlation, the correlation between the true high-res field and the emulator and this thing, the super res. The super res here on small scales, say below k=1, is really bad because we know the small scales are generated from random noise, right? So you wouldn't expect them to match. And here's the emulator. You can see all the way down to k=10. It's actually less than 5% different from the true Fourier mode. Okay, so it's got better by an order of magnitude, right? So that's what we want. K equals 10 is pretty good for nonlinear scales, right? On for those of you who know about these things.
Can I ask? So you have only modified the loss function here, or what?
Yeah. So okay. So there's a discriminator, right? There's the whole full GAN that with a discriminator and everything, and then at the end, there's an additional layer which Owen can talk about later, and you can talk to him about his poster, which basically moves the positions of these small halos around, and then there's a loss like an L2 loss which matches, which has to decide whether it's matching well enough or not, right? And so you weight these two, the discriminator loss and this other loss, or an L1 loss, I think it is. You weight the two losses and you try and balance it, right? So, you can't get it perfect either way, but there's a good balance where you might be able to do what you want. So I don't know, you can ask Xiaowen, he's sitting at the back there, but okay. So like I said, as the output from the super resolution has the same format, we can evolve it forward with an n-body code. And so this was done by Ankita Dasgupta, again, a summer student last year. So what happened was we evolved with the GAN, basically super res to redshift of 2. And then we continued onwards to redshift of 0 using the super res GAN, and also with an n-body code from redshift of 2 to redshift of 0. And I thought maybe the result from the GAN would sort of explode or something. We weren't clear whether all the velocities were consistent or whether the clusters were actually virialized. You don't really know, right, until you run it. And it was fine. So here's the true high res after evolving from redshift 2 down. Sorry, not the true high res. It's just this step evolving from redshift 2 down to redshift 0. And then this one is evolving from redshift 2 with the AI, and they're pretty similar, right? Again, the halos mass function is within 5% and so on. So they didn't explode. Okay, so that was gravity and dark matter, but you can imagine people do simulations of all sorts of other physics. And so, okay, this is my little thing from before. You want to be able to simulate all physics. What do we want this thing to do? Okay, and so here, some nice recent work with hydrodynamics. And this is one low resolution NICS code doing the intergalactic medium. And again, compared to a high resolution, and you've got a target which was used to make Lyman alpha forest spectra. And looking at the intergalactic medium, that's a good use case again for this, because it's a simple physical system. You don't have to worry too much about star formation and other things and feedback. And so here there's some summary statistics from this work by Jacobus et al. Looking at the flux power spectrum, for example, output from their generative model compared to, here's a low resolution simulation, which, you need to be able to resolve the thermal broadening scale in the intergalactic medium. It's like 100 kiloparsecs. It's difficult to do in a simulation that's 100 megaparsecs in size. And so this is a really nice way of doing that. Okay, and supposing we want to go to even smaller scales, what about turbulence? What about star formation? What about things like that? What can we do? So here, I decided to look at some other field outside of astronomy, right? So you might, know about Formula One, you might know that Honda won the World Constructors Championship. At least their engine won this year, and they've won before. Turns out that the guy who does the modeling for that actually uses physics-informed super resolution GAN to actually enhance the modeling, right? So here you're doing turbulence and combustion. Okay, it's not something we do too much of in cosmology, astrophysics, but here's just a picture from one of their simulations. So here's the air fuel fraction, okay, like density if you want, and then here's the dissipation rate. So one thing is combusting, okay, and these turbulence simulations, they're all done accelerated a factor of 10,000 times faster than they would be using neural networks. And that's how it was possible to simulate. You might ask, okay, do we have any use cases in astronomy where we've actually done something, right? So this team won the Formula One World Championships, right? So they actually got their neural network to do something useful, right? So that could be an inspiration for us, I guess. And the way it works, you shouldn't read this, but basically for every time step from his low resolution simulation, which they call large eddy simulation in turbulence, basically you reconstruct the small scales with a GAN, and then you feed that back in and you evolve it forwards. And apparently you can do that for thousands of time steps and it works out really well. So here's, for example, the kinetic energy and the dissipation rate. This is what would happen if you had a low resolution simulation. Once you enhance it with the GAN, basically you recover. This is a function of time. You recover. And apparently, because turbulence has this sort of universal character on small scales, that's basically why it apparently works well. But of course, turbulence in astrophysics is not any different. And so there's some hope for doing this in, say, star formation simulations. Okay, so talking of star formation, there is some work that's been done on, for example, supernova feedback. And so here's some work where there's in a large-scale simulation with particles in it, those particles are being assigned to a grid, and then small-scale supernova explosion simulations that were grid-based were then reassigned to the particles using Gibbs sampling, and then put back into the simulation. And so this is a way of doing subgrid. I know we've talked a little bit about doing subgrid. And so this is one of the first attempts at putting subgrid star formation. So very learned, very high resolution star formation grid simulations into a cosmological simulation. And here are some results just showing that the thermal energy, this is what you would get if you just stayed at the resolution of the simulation, 10 solar masses per particle, and you don't get a good result compared to the true thermal energy. But then putting in this Gibbs sampled learned subgrid model apparently gives you a better slope here, so you get the correct thermal energy. So that's nice to see. Okay, so let's now talk about something you actually would do with a simulation. People want to do inference, okay, and so they want to trust the results. They want to come up with uncertainties that are quantified and so on. And so there are different things you can do. And we've heard a lot about this, and there are many other talks about this. But in the context of deep learning, basically you want to use the neural network to approximate this function that goes from your observable to whatever your parameters are, right? And so people use different architectures, normalizing flows, and things like that, right? And again, all of this uses simulated data and training data and so on, right? And so I'm not going to cover in great detail simulation-based inference. There's huge amounts of work, but I'll give a few sort of examples, recent work. So here's this framework, for example. It's called SimBig, and the idea is here not to use hydrodynamic simulations, but to use a halo occupation distribution formalism to make forward models. And then this has been applied to observational data. So I don't think there's too much that has been applied to observational data. This is one of those forward modeling of SDSS BOSS data to infer parameters, for example, cosmological parameters. And so the people doing this work, they tried, again, to test the robustness of what they were doing by saying, okay, let's train with different models, different forward models, and see if we get the same parameters, which we marginalize over the things that we don't want. And in this case, lots of these parameters, Hubble constant, spectral index, and so on, worked out well. They noticed that sigma 8 basically didn't. There was a bias depending on which simulation models they used out of these models. And that bias could be removed as long as they stuck to fairly linear scales, removing these nonlinear scales, right? So again, this is a pattern that we'll see trying different simulations that you were, testing on different ones that you were trained on and seeing what biases you get, okay? And so here's, okay, the sort of ultimate so far simulation project here, camels, okay, which we heard from before and I mentioned before as well. So here's just the same region of the universe simulated with 3 different forward models, here 3 different hydro forward models, and also in body codes, I guess, underneath it. And these are the different galaxies that come out. And I guess I'm not going to cover too much, but here, for example, again, you can train with a different forward model And here, this is a recovery of different cosmological parameters. Here, omega matter and sigma 8. And here, where the model was trained on, say, the Simba Hydra model and then tested using Illustrious. And, it does really well. This is, just a few percent different from the truth and within the errors. So that's really nice. There is some lack of robustness that's been seen, I guess, in some of like Paco's recent work, where basically tried to measure parameters from a single galaxy. So, I guess, you can't do much better than that unless you do it measured from 0 galaxies, like just making it up completely with no observations. So this is, as good as you can do. And it really works amazingly well. Like you can measure omega matter from a single galaxy. There is some lack of robustness here, though, again, using different forward models. So that if you know how the Simba model does feedback, Ramil Dave is big into feedback, and so all these galaxies are flying all over the place. And so, there's a big difference between the baryonic effects in some models and others. And so that also then affects the dark matter. And then if you're trying to measure omega matter, you're influenced obviously by what most of the matter is. And so that's the dark matter. And so, that's something that needs to be understood. And I guess, Paco's thought about it a lot. And so, that's things that we need to do. Okay. So again, robustness here, trying to measure the warm dark matter mass. Here's slices from simulations, the ones with hotter dark matter, obviously more smooth. And so here you can see that you can train and recover the true mass up to a certain point, and then you don't have any. Once it gets too massive, then you just can't tell them apart anymore. There's not enough smoothness for the neural network to pick up on. Okay, you can go backwards. You can do field inference. You can go from the stellar distribution to the dark matter distribution. And so this is some again recent work here. Here you're marginalizing over astrophysics. As usual, need lots of training data, but I guess it is kind of nice that this is the input, pretty sparse galaxy data, and then you end up with a prediction for what the dark matter distribution looks like. And so there are quite a few people who have done that. There's also work about going backwards in time to the initial conditions. Let's see, okay, 1D data that I like is the Lyman alpha forest. So here's some work where you've got a Lyman alpha spectrum. Then when there's a quasar heating, the spectrum is kind of smooth. And then this is this region here. And you can basically predict what the temperature is. But again, you have to include a large grid of training data. So here's another piece of work where this is their training data grid. And you can see every point here is a simulation with different parameters, the mean temperature and the slope of the temperature density relation. Again, do we have enough training data? Doesn't include noise, doesn't include astrophysical instrumental systematics. So, we really have to think about, can we include all that? Okay, so I guess I got too much stuff, so I'm going to kind of fast. But anyway, so differentiable simulations are very useful. Remember, we're trying to actually figure out what's going on using gradients. And so we need to use automatic differentiation that we have in our deep learning frameworks to our advantage. And a really nice example of this is FlowPM. So basically, you can reconstruct the initial conditions. And here's the cross correlation of the Fourier modes again, doing well. And then one issue with these differentiable simulations is that you need to save all the states of the simulation in time at every single time step in memory. So you're limited to maybe 10 time steps or 50 maximum. Okay. But there's a nice paper by Yin Li recently showing that, in fact, you could use some variables, the adjoint variables that are dual to the regular variables, and they evolve backwards in time. So to compute the gradients, you only need to evolve the simulation forwards, and then you can go backwards using the adjoint equation. And so as long as you have a reversible process, which you do, then you can just do this and you can save all the memory. And I think that's really a nice thing. Okay, so I'm almost at the end. So one thing that we haven't really talked about that we wanted our machine to have was trustable, explainable, and low energy use. Okay, I'm going to defer through a lack of time we had a conference at Carnegie Mellon 5 months ago, Responsible AI, and there are a lot of talks. You can go to the website and you can see some experts, for example, in trustable and explainable AI, and the talks are online. One fun thing was we had a human versus generative AI competition, and I encourage you to try it out yourself and see if you can beat the winner, who was a math professor from the University of Minnesota, she got 72% correct. Okay, there are no prizes left, but you can still get the bragging rights. They're all things that were submitted by people at the competition. Okay, they submitted either text or images. I'm going to show you just images, but this is, there is a lot of text there too, and you have to decide if it's AI or real. So I don't know. Tell me, is this a real galaxy or is it a DALL-E or whatever galaxy? What do you guys think? Shout out if you think it's one or the other. Fake. We have fake. Okay. Fake. Okay. Have you never seen a galaxy? All right. This one, real or fake? It's not a galaxy. Okay. It's real. Okay. So we had fake, real, and then this one, fake. Okay. Fake, real, fake. Okay. It was actually real, fake, fake. Okay. So you got the first two wrong. Yeah, I think this one only has 4 legs or something, so it can't be one. Anyway, so if you thought that was fun, have a look at the competition because you can test yourself. And 72% was the winner. Most people got random. So I think that was a random winner anyway. Okay, so the final thing, I guess we've talked about the issues with energy consumption, global warming, and we're here not in Paris, because Paris sucks and New York is much better. Is that right? No. Anyway, so we're here having fun in New York, and we saved a whole bunch of flights, CO2. This is some nice study done by Stevens et al. It's for Australian astronomers, but it probably holds for French or American astronomers. And you'll notice here, as was mentioned by one of the speakers this morning, supercomputing, enormous amount of the CO2 use. Okay, and you might say, how much is that in something I understand? Well, if you're an American, you understand this, right? So if you had these 3 cars in your garage and you drove them for the average amount, which is 14,000 miles each per year, that's how much is equivalent to the average astronomer's supercomputing use in Australia, right? That's not the supercomputing use of somebody, like many of you. I don't know, I'm part of a grant where we have 100 million core hours. That's actually equivalent to tens of times more than that. I did do a translation for the French people as well. It's equivalent to 39 of your pathetic little French cars that you drive around. And French people drive less, and also the gas mileage is different. But anyway, all right. So so serious point, I guess. I mean, that's actually more than I thought. I mean, I have a small car, not a small blue one, but I thought if I drove this, I'd be really obnoxious. But it turns out I'm much worse than people who own fleets of these. So it is kind of scary, right? Okay. So there is definitely room to improve, right? So here's the world Go champion. He beat AlphaGo a few times before it got improved. Okay, with 20 watts of power, AlphaGo was running on a megawatt. Okay, so there's definitely improvement that can be made. Okay, so how could you use your reduce your carbon footprint? So obviously try and use pre-trained models. Many people train something and then they throw it away and start again. Okay, there is actually tools you can use to track your CO2 use that you can actually use as a Python code that you can apparently seamlessly use. I haven't tried it, but it tells you how many kilograms of carbon your code is used. If you train your models during the day, it turns out the energy is much cleaner when there's solar power, particularly in this country. And you probably know this already, be more efficient with your hyperparameter searches. Okay, so my last slide. Okay, so one of the questions you might have is, what can we use these generative simulations for, right? Are we actually going to do everything that we could do with a full physics simulation? So if we think we can't, then we can use them to make mocks, for example. So mocks simulations, as long as the observational systematics are more important than the ones that we get out of our simulation modeling, then that's fine, okay? And I think a lot of the people who are using these models are using them for mocks, okay? Again, subgrid modeling, what subgrid modeling do we have in our simulations right now? Okay, star formation. Many people are using sort of 20-year-old Springler-Herquist, for example. There's a few parameters in there. How do they compare to what's really going on in a star formation simulation? I think we can definitely do better using deep learning, okay? Apart from that, we need to be sort of careful, right? So simulation-based inference, okay, we'd like to be able to measure parameters. We also want to extract knowledge somehow. We need to explain basically what's going on. And a good start is already these astrophysics parameters that say camels is constraining. What about positive and negative things, right? We still really haven't decided how much training data is enough and how to quantify that, right? We always want to train with less. We also want to make pronouncements about how well we've done with less data, and it's difficult. So I guess we really have to figure that out. But positively, there are a lot of things that we can do with scientists, right? We have analytic models, we have physical understanding, we have obviously hundreds of years of physics textbooks, right? And so we actually have ways to test things that we couldn't if we were working in, psychology or marketing or whatever, right? So, for example, we have analytic models for our summary statistics, and we can actually test and inform our deep learning approaches using those, okay? So, yeah, so I'm positive about this. That's my end takeaway. All right, thank you.
Thank you. Time for questions. While people think about it, let me also directly come here to your conclusions and brief this opening thoughts. I guess, what do you see as the likely cosmology equivalent of winning a world championship?
On, please?
Yeah. Is it on? Can you? It is? Okay. All right. So you were saying, what is the cosmology equivalent
of winning the Formula One World Championship?
Oh wow. Yeah, okay. It's difficult, but we're all here to discuss things. I don't know. Do people have any ideas what they think? What are they working on that in the back of their mind they think that's what could win?
Yeah. What's the deep learning enabled discovery that wouldn't be possible otherwise?
Yeah.
That you see coming.
If I knew, I'd be doing it, I guess. So I don't. Yeah, it's a very tough question.
So you started at the beginning saying that you would like to simulate the entire universe with single atoms.
Sure.
How far are we? Realistically.
Sure. Okay. So, all right. So it's something that I've done for like classes and stuff, right? You can obviously extrapolate so that the graph that we showed there, number of particles in the simulation, you want to extrapolate until you get to 10 to the 90, right? It's exponential. It's been exponential for the last, 50 years. And so if you keep going to the year 2350, that's where you would get to that you're simulating the entire atom at one resolution. But obviously you'd need a universe to simulate the other universe. So you have to find another universe first. So, but yeah. So we're not doing too bad. It is exponential all the way. So yeah, I mean, we're hoping, that these techniques are gonna mean that the slope, that things will go faster, right, even than that. So I guess maybe that's the ultimate goal. I think in this compilation, sorry about this, but in this compilation, there's that Florent did. He put this sort of post 1990s, post 90s super exponential trend. Okay, this thing. Okay, so maybe if we start using deep learning accelerated simulations, we'll have an even steeper thing, right? And so it might not be 2350, it might be 2200 if you can wait that long.
I hope it works, yes. What is the prospect of having this kind of like deep learning improved subgrids that are going on the fly? Basically, when I start a simulation, that it tries to figure out what are the self-similarities among different structures that I don't have to pre-train?
Sure. Yeah, that's something that I think a lot of people are working on. I think we're pretty close. So it's, like I said, with the subgrid models we have now are very crude. So any sort of advancement over that is good. And, you saw there was something that had been done already with supernova feedback. And I think there'll be other, I think we're working on that too, that there'll be other things that will come out pretty soon. If you're running a simulation, feedback feeds from the smallest scales to the largest scales, right? And that's the problem you have, right? If you just have a way of generating things without doing it on the fly, you're never going to capture that, right, properly. So I think, this is obviously a good use case, and I think that's going to happen, right? There's not really physics in the current subgrid models anyway. So people who complain about that, it's a black box in deep learning or whatever, you're not really losing too much anyway. So yeah. Oh, thanks.
Just building on that black box comment you spoke earlier as well. Imagine that you had a really good emulator, put in some beautiful subgrid physics and like subtle difference in expected physics, and you have the potential to know. Would you believe it? How would you ever know?
Sure. Yeah. So that's the big question, right, that we have to deal with. Right. And that's why, I'm constantly saying, how much training data do we need, right? We don't really know. So the argument you could always make is you just have to simulate it at full resolution, right? So maybe.
And why bother?
So sorry.
I mean, why? To what purpose the emulation then?
Sure. Exactly. So that's what the response always is, right? And I can see where that's coming from, right? So you might say, okay, maybe the emulation is to cover a giant parameter space that you couldn't do efficiently. And then once you've honed in on something, then you run it properly, if you like. But yeah, obviously it's, if we're doing science and we're not just making nice pictures, then we always have to confront that. So yeah, so I don't know. I think that maybe that's why people haven't actually come up with something yet. Sure.
Thanks, Rupert. I like the combination of machine learning and human learning. But I mean, I have a question which is along the same lines. So sometime in the near future, we're going to have people claiming parameter values based on machine learning. And are we, it's just unclear to me how the debate goes, whether we even have the tools to articulate how to decide whether we believe the results or not. So I mean, it's not even that that I'm not going to believe the results. I'm not even going to know how to decide whether I believe the results. So how do we have that debate? Because it's coming soon, I think.
Yeah. So I was debating myself whether I should put like Hitchhiker's Guide to the Galaxy, the answer is 42 or whatever, but I thought with this audience, I'm way older than everybody, nobody would get it or whatever. So sure, we might have some pronouncement and then
I would get it. Like, second funniest Douglas.
Okay, sure. That's a good one. So yeah, I don't have an answer to that. I mean, it's something that we all have to wrestle with, right? Sure. What can you say? I don't know.
Just worried that we don't even know how to have the debate.
Sure. I think somebody here should volunteer. We don't tell anyone outside this room. Right. Just come up, just say, okay, I have measured using machine learning. H0 is actually, 92 plus or minus 0.01. Okay, and just put it out there and say, okay, this was done with Google's proprietary, model, which is not publicly released. And then, and see what happens.
I just want to say that on Wednesday, the debate will be precisely about this.
Okay, excellent. So you'll find out on Wednesday. You only have to wait 2 days, and then you'll know.
There's an H0 debate on Wednesday?
You believe what you get.
And then we write papers for April 1st.
Hi, great talk. Thanks. I guess at the start of the talk, you also kind of mentioned like you were like, okay, so most of the people in this room do one of two things, right? I guess where do you think like that kind of like divide comes from? Like, why are these two fields where we're seeing most of the machine learning applications in astronomy, and why hasn't it like propagated into all of the fields within astronomy?
Because we're smarter than they are. I don't know. Yeah, or more stupid. I don't know, as Douglas would say. Yeah, I mean, it has, I guess, to some extent. I mean, there are definitely examples of people doing exoplanet research with a lot of machine learning, including simulations of planet formation, for example. But yeah, I don't know, maybe there's something about the sort of grid. I'm just trying to think now, like the grid-based nature of cosmology simulations. It's some sort of like an image grid or something like that instead of objects. I don't know. Yeah, I'm not really sure. I'm not sure how many people here are from outside of cosmology. Like, what is the fraction, you know, like at this conference? Do you know? Did you ask people what their research interests were, Paco?
So we choose not to be everybody cosmology. So
Yeah.
should be a.
Yeah. Sure. I see. Okay. Okay. Of course not. Just tell the truth.
Thank you for the talk. So I guess coming towards the end of your talk, when you were saying, you know, like for environment, like use pre-trained model, like if possible. I don't know like how general it is for everyone, but right, like different people are coming up with emulators and like there are different simulations you have and everyone is saying mine is better or like use mine. So if you sort of like, what prescription would you then offer someone is how do you kind of like make that decision tree to even go and decide? Because I think what I feel is that like if you try to go and do inference with one emulator or simulation, you get H naught to be X, and then someone else's tool gives you some other answer.
Sure.
And so as a community, like how do we agree which like how to decide which pre-trained models are the ones that we trust?
Sure. Okay, so let's go back a few years, right? And you know, how do we decide that we should use gadget as an embody code, right? I'm not sure how we decided that, right? But you know, that's turns out that most people do use that. So we need to have some sort of competition, and then you know through that people decide what they believe, and maybe it's a more difficult problem, and the one you're describing is more difficult. But I don't think we have a clear way of doing that. You know, gadget definitely gets some things wrong, right? There's some issues, you know, with every code, there's different issues, right? And I guess people are never so altruistic as to say, okay, I'm going to stop doing my research and then just for the good of everybody, I'm going to figure this out. And people wouldn't listen to them anyway. So yeah, it's a difficult problem. I think as long as people, there's different sets of people doing things and having different answers, that's healthy, right? And that's how we know. If we get to the point where there's only one inference machine, everyone is like, okay, we go back to Douglas's question, right? We're all like, how do we believe this machine? So yeah, again, it's another thing that maybe you'll debate on Wednesday, I guess.
Yeah, so also thank you for the very nice talk. And sort of riffing on some of the questions that have been asked, like the Formula One example, that's a nice demonstration where like they had some physical problem that they could apply their model to and demonstrate that it worked correctly because it produced the fastest race car. And I guess in cosmology, one of our limitations as our training set is almost always going to be from simulations. And so there's sort of a tension between, can we build models that describe the simulations well enough, and can we build simulations that describe the data well enough? So sort of based on this high level picture you've given us here, do you think the work that needs to be done today skews more in the direction of our modeling techniques don't do a good enough job of doing like super resolution simulations based off of what our simulations can tell us? Or that fundamentally our simulations, like for example, that nice little same big comparison, just don't understand well enough what's happening at this high resolution level And so even if you had the ideal model that could reproduce the results at different configurations of the subgrid physics, that wouldn't necessarily help you because the thing it's reproducing isn't quite good enough yet.
Okay, so there are models that can do much better than the ones that we've tried to use in, because they're much more expensive to run than the ones we use to do simulation-based inference, right? So I don't know if you've seen like Phil Hopkins's work where he simulates a accretion disk around a black hole from cosmological initial conditions, right? So there's definitely, we can do the physics, I think, much better than what I've shown you here, right? How that can translate into actual comparison with data, right, and actual inference is not clear, right? But yeah, so yeah, there needs to be progress on both sides. I don't really know what the answer is, sorry, but yeah, I mean, it's again something to think about. Sure.
Let's thank Rupert again.
Right, thanks.